In this video, we present our work, Online Multi-Contact Receding Horizon Planning via Value Function Approximation. When deploying legged robots in the real world, robots can encounter unexpected disturbances, such as environment changes and state drifts. These disturbances often cause the original motion plan to become invalid, and continue executing the motion can lead the robot to fall. To ensure reliable operation, it is important that robots can online replan their motions. To this end, receding horizon planning can be a promising solution. Receding horizon planning, or RHP for short, refers to the planning method that aims to constantly update the motion for immediate execution, based on the state of the robot and the environment. Typically, receding horizon planning often needs to incorporate a prediction horizon that foresees the future beyond the execution horizon. This prediction horizon can be seen as a value function approximation, which guides the planning by estimating the future effort required for completing the task, starting from different robot states. However, approximating the value function with the prediction horizon can result in expensive computation, which hinders online usage, especially when planning multi-contact motions where complex nonlinear dynamics is involved. To enable online multi-contact receding horizon planning, in this work, we explore the possibility to simplify the computation for approximating the value function. Following this path, we firstly propose multi-fidelity receding horizon planning, in which the execution horizon is planned with an accurate dynamics model, while the prediction horizon is computed with a simplified model. This ensures the execution horizon is always dynamically consistent, while reducing overall computation complexity. We implement the idea in planning contacts and centroidal trajectories for multi-contact locomotion, and we compare three candidate approaches. For our first candidate, we employ the centroidal dynamics model in the execution horizon, while in the prediction horizon, we only consider the linear center of mass dynamics, and ignore the dynamics of the angular momentum. During our tests on uneven terrain, our first candidate always fails to converge after a few cycles. This suggests that considering angular dynamics in the prediction horizon is important. For our second candidate, apart from the linear center of mass dynamics, the prediction horizon also incorporates a convex relaxation of the angular dynamics. Compared to the baseline which computes the entire horizon with the accurate model, our second candidate demonstrates better computation efficiency. For instance, our second candidate achieves 69% of the cycles computed online, where in these cycles, the computation can always converge within the time budget, the duration of the motion being executed in the current cycle. In contrast, the baseline only has 51% of the cycles computed online. To further improve the computation efficiency, we present our third candidate, where the prediction horizon remains to consider a convex relaxation of the angular dynamics, but we switch the rectangular foot model to a point foot model. This can reduce the decision variables of the planning problem. From our experiment result, we can find that our third candidate achieved the best computation speed, where 75% of the cycles achieve online computation. We further test our multi-fidelity approaches on more challenging terrains, for example, the large slope case where the robot cannot maintain static stability and has to traverse the terrain dynamically. Unfortunately, we find our multi-fidelity approach can fail to converge for about half of the large slope terrains. This suggests that the convex relaxation may lead to inaccurate value function approximation for these challenging scenarios, and further investigation is required. Alternatively, to achieve online receding horizon planning, we can also shorten the planning horizon by approximating the value function with a learned model. However, learning a value function for the multi-contact problem can be challenging. The main difficulty comes from the fact that value function is defined in a coupled state environment space, which requires a flexible parameterization to capture the landscape changes of the value function with respect to different environments. To deal with this issue, we propose to learn an oracle to predict local objectives as intermediate goal states for completing a given task, based on the initial robot configuration, goal state, and a local preview of the environment. We then construct local value functions to attract the execution horizon to approach these local objectives. We call this approach as locally guided receding horizon planning, or locally guided RHP for short. We test our locally guided RHP on uneven terrain, and we demonstrate that locally guided RHP can achieve the best computation speed compared to the baseline and the multi-fidelity RHP, as 98% of the cycles achieve online computation. We also test our locally guided RHP approach on the large slope terrain. Despite the scenarios become more challenging, our locally guided RHP can still achieve 95% of the cycles computed online. To further demonstrate the efficacy of our locally guided RHP, We also perform real-world experiments in changing environments. For example, during runtime, we can switch the far end of the current environment, from a flat surface, to an up and downhill terrain. Such changes make the pre-planned motion invalid, and online updating of the motion plan is necessary. Owing to the fast computation, we demonstrate in the real world that our locally guided RHP can successfully achieve multi-contact locomotion planning in an online receding horizon fashion. This means in each cycle, the motion plan for the next cycle can be always computed before the robot finishes the motion execution of the current cycle, while considering the latest environment model perceived by the robot. This allows the robot to successfully achieve reliable locomotion in this changing environment. In our experiment, we implement terrain perception with the Vicon motion capture system, where we use the position of a Vicon marker plate to identify different states of the environment. Furthermore, we also test locally guided RHP in another changing environment, where we add a stepping stone along the pathway. In this case, our locally guided RHP successfully achieved online computation for all the cycles, which allows the robot to safely climb the stair. Lastly, we test our locally guided RHP on various of uneven terrains. Same as in previous cases, our locally guided RHP also achieved online computation for all the cycles. Thank you for watching the video.